So good day to everybody who is already online. My name is Wolfgang Wagner. I'm from the Technical University in Vienna, and in this webinar today, I will tell you about our approach for combining optical and SAR data for mapping of water bodies and floods. So before I start the talk, I would like to acknowledge my team who have contributed to the talk. Basically, it builds on all the research that we have conducting, and for this talk in particular, I would like to thank my colleagues David de Vesta, Mohamed Hassan, Florian Roth, and Bernhard Bauer-Marschallinger. Also, many thanks to our different funding agencies. In particular, there is a European Space Agency who is also funding the EU Africa program, but also to the Copernicus program from the European Union or the European Commission itself. Also there we have had some national funding to carry out our research on water and flood mapping. So before I go into the topic of how to map water and with Earth observation data, both optical and SAR, I want to first motivate a bit why we are doing this. And I would like to point here to the latest State of Global Water Resources report from the World Meteorological Organization, which showed that in 2024, around 60% of rivers globally showed either too much or too little water. So basically showing that something is going on in the hydrological systems. And it's also now a repeated year in a sense that the conditions are not as usual as expected. Overall, with increased warming, 2024 was too dry and hot, but there have been very strong differences between regions. So some regions have suffered drought, others have seen enormous droughts. So the WMO is also calling for improved monitoring of water resources, using, of course, all kinds of sensors, both from space and monitoring on the ground. This here is a very nice graphics that shows the river discharge for different river systems globally in last year. So it's showing the mean river discharge and the deviation from the past. In the graphics below, you see how to interpret the colors. So if you have here this greenish colors, dark greenish colors, that means last year has been much above average discharge. And if it's the reddish colors down here, then it means it was much below average discharge. And we can see that actually most of the catchments show normal conditions, but the number of catchments with above or below average conditions are quite many. We've also seen in recent years that in some regions there have been increased flood risk. For example, if we look at Europe, we have seen a number of very serious floodings, in particular in the Mediterranean regions in recent years. Here are two flooding cases that were caused by the storm Daniel that was charged by very warm water temperatures above the Mediterranean. So there was high humidity in the ground, the soils were dried out, and then due to the ensuing intense precipitation, there have been enormous flooding in both Greece and in Libya. Now on top you see here the flood situation in Thessaly in Greece, where many agricultural areas have been flooded. And here in Libya, there was the case that there was significant rainfall in the desert areas, and then there was a dam break and hitting the city of Derna in a very bad way. But also this happened in the year 2023. But when we also look in 2024, there was significant flooding in Austria to Poland. There was also the disaster in Valencia, Spain. And this year, we had recently flooding in Bulgaria. At the same time to having an increased flood risk, we see an increased drought risk. That's just stemming from the fact that there are increasing temperature leading to increased evapotranspiration. Plus, what we're seeing is that atmospheric patterns have been changing. So, for example, in Europe, we have been seeing atmospheric blocking that have led to longer duration of certain weather patterns. that have led then to drought scenarios. As you know, talking about drought is not as simple as talking about flooding. It's a more complex process. We start from when you look at anomalies in precipitation, we talk about the meteorological drought. If then this is affecting the water in the soil and crop production, we're talking about an agricultural drought. And if it finally arrives in the river systems and in the water reservoir, we talk about a hydrological drought. And again, here an example from Europe, in this case in Sicily, where we see here the use of Earth observation data to monitoring the change in surface area for this lake in Italy, where often, it can be filled during good years, but particularly to 2024, 2025, it was really low. Another example for what this could mean in terms for the environment, I show here an example for Austria. This is a wetland area and the lake Neusiedl. Around the lake, there's wetland areas. This is reed. In 2022, the lake water levels were so low that many areas within the wetland area here were completely dried out. This is then being seen by increased backscatter from that area. So water has all disappeared from those parts, having effect on the ecosystem and on bird life in those areas. Yeah, if we look into how our capability for mapping water bodies and floods have changed over the year, we can say, well, the breakthrough was coming through the Landsat program, which has been delivering since the 1970s data, but in particular with the launch of Landsat 5 in 1984, we're starting to have data at a rather good spatial resolution, good spectral resolution, and with sufficient revisit time to allow us good mapping. And of course, what's also very important is that sooner or later these data were given free, so that everybody could start using it. So on top, we see the sequence of the different Landsat missions, and below we see how the spectral characteristics have changed from Landsat 1 to the latest Landsat 8 and 9 missions. Right now, the question is how the Landsat next generation will be looking like. This would be the current plannings as before the Trump administration, and currently the discussions to be rescoping the full mission to more align with what we have been knowing from Landsat 8 or 9. Given the big wealth of information that's contained in the multispectral data from missions like Landsat, it's very straightforward to map water body in some sense. The idea is quite simple. So we have our channels at different spectral bands, and each type of surface has a certain characteristic spectral signature. For water, we can note that overall reflectivity is rather low, but still a bit higher here in the optical domain, and then decreasing rapidly in the infrared domain. So in principle, you can take one image and transform this into an output image showing, for example, different type of land colors like water bodies, grassland, forests, urban areas, and the like. The first one to show that we could actually do the systematic mapping of water bodies on a global scale has been the team around Speckle, who published in 2026 in a paper on Nature, using build on the capabilities from the Google Earth Engine, where they used all Landsat images from the Landsat Mission 5 up to the present to map water bodies. Essentially, when we look now at the method, it was still quite of a straightforward method. It was based on an expert system with threshold segmentation. There was still some empirical inference in how the different land cover types were used, and then there was also some post-processing to limit wrong classifications. Yeah, the result was quite spectacular because it allowed us to have a very detailed view on how dynamic water surfaces can change on Earth. Yeah, it's just one of the images that were shown in the original Peckel paper from 2020-16. So while as useful optical data are for mapping water bodies, there's obviously one problem. So if there are clouds, we cannot see through the clouds, so we cannot observe the land surface and the dynamic water bodies. This is just highlighted here by one case that shows a flooding case in France from December 2023, where in the right side image, so the image from Sentinel-1, we see distinct flooding pattern here along the river. Obviously, if we looked at the corresponding Sentinel-2 images, we only see clouds. So that's one major limitation of optical system. A second major important limitation, which is somehow often overlooked, is the fact that optical data have only limited capabilities for mapping water, because, for example, if we have water below a dense canopy, we cannot see it. So most people take like optical images and they map the water surfaces visible within the image. But what they are not doing is to actually highlight those areas where mapping is not possible because of those limitations. Yeah, this is the purpose of this slide, where I confront the water occurrence map from Landsat, as shown here on the right, over the Amazon region. Obviously, it's dense forest area, and we see only along those areas where the canopy is open, where we can see the water, and that can be, for example, confronted with new measurements from GNSSR reflectometry data, where we have a bistatic measurement configuration and working at microwave frequencies, where it's much more straightforward to detect surface water below the canopy. Yeah, basically here, if you look at those colors, so these violet colors show you very strong reflections from water below the canopy, and you can see how much more water below the canopy that can be seen with this technique. So that technique is very nice, but one downside is that the original resolution of the initial measurements is very low. So actually, yeah, it's very nice to see through canopies. On the other hand, the spatial effective resolution is much, much lower than we have for the Landsat data. Yeah, and the last case, well, the last problem is over detection. So also with optical data, as with SAR data, obviously there's classification errors in the data. And I would just like to show this here with one very common index, the so-called normalized difference water index in WI. That's the difference between green and near infrared divided by green plus near infrared. And we make a plot of those index. We see obviously very nice pattern. We see that here those lakes in northern Italy show up very nicely, but it's also apparent that this index is not a simple no water decision, but there's all kind of different values in between. So that's actually possible to start confusing it and leading to wrong classifications. Some areas also show very strong spectral characteristics similar to water surface. So for example, if I just would use the NWI and I would make a plot of the river here and the airport area around Malpensa, then we would see that actually also the Malpensa airport might be mapped as a water surface area. So now the question is, how can we combine optical and SAR data to overcome limitations of each data source? Yeah, so the expected advantages by combining optical and SAR data is that we get a more complete coverage of surface water dynamics, both in space and time. And the expectation is that we can leverage the information content from each source to have less under detection and less over detection. Now the question is, how do you do this? A very straightforward approach is if you use the level 1 data from the optical data, so either Landsat or Sentinel-2 or any other high-resolution optical system, and then you take a SAR image, the backscatter images from there. You make an image stack so that you have quite a diverse input data set, and then you input this into a certain classification algorithm. Nowadays, these classification algorithms are more and more machine learning techniques like neural networks or support vector regression and the like. You also use training data from field observations to have some training, and then you make your classification. So the potential advantages of this approach is that thanks to the higher dimensionality of the input data set, that you get a more robust classification that also achieves a higher accuracy than if you would use each data set by itself. A disadvantage of that approach is that the optical and the SAR data are often not acquired at the same time, which might mean you're not seeing the same surface water area. Another disadvantage is you might get a very good result, but the output is not really traceable to the input features. So if something goes wrong, it's very difficult to reproduce actually why the classification has given you the wrong result. And last but not least, you have to mention that if you want to do this, you have a high data preparation effort because you need to bring all the data in one specific place. You need to carefully co-locate them. So that meaning that the geometry of all input data sets is the same, and that you also apply all the best standards on the radiometric calibration of each of the input data sets. An alternative approach is that you combine the data by not combining the level 1 data, but by combining interpreted water body and flood maps that have been derived individually from the optical and the SAR data. So that's illustrated here. So you have here a water body map from Sentinel-2, a water body map from Sentinel-1, and you combine them and somehow you get a map out of it that has much reduced over detection. Here in this case, it's not really true that the river becomes more sharper, but certainly you have reduced errors in the over detection. So the combination could involve using just the overlay of the binary classifications, or what we will argue, or what I will argue here is that it's better to use likelihood values that are derived individually from the optical and the SAR data. So the advantages of this approach is that you can go to rule-based fusion or aggregation methods, where you can use your knowledge about surface water dynamics to make decisions of how to combine the data. And overall, if something goes wrong, the outputs are much more traceable. And you also have less data preparation efforts because it's not necessary that you move data around to one common place. But for example, you could do the classification of the optical data on one cloud platform, for example, on the Copernicus data space ecosystem of the Copernicus program, and you do another work on, for example, on the Amazon Web Services. So you make on those platforms the classification, then maybe you fetch the data from there, load it up to your computer system, and that's already much less work than before. Potential disadvantage of this approach is that overall the classification is less robust and that you have higher classification errors. But of course, the work and the strategy would be to make that system as good as possible to make errors as little as possible. This approach for combining optical and SAR data has been inspired by our global flood monitoring service that is being run based on Sentinel-1 data in an operational way. So please allow me now to introduce that service a bit more in detail. So this service is being run as part of the Copernicus Emergency Management Service. The component itself is called the Global Flood Monitoring Component, which uses the Sentinel-1 mission that has, for most part of its time, consisted of 2 satellites and its systematic coverage to do fully automatic processing of all incoming Sentinel-1 images within 8 hours. Traditionally, the idea has been, well, there's a flood, let's get an image, let's do some expert interpretation, produce a map of flooded areas, and then present it to the user. In this traditional way, you lose lots of time due to the human influence in the whole processing line. So the big advantage of the GFM service is that no time is lost due to human intervention. And also, if there's like unreported flooding events, you still see them in the data because everything is processed automatically. A big disadvantage of that approach is because most of the images will not show any flooding. So for example, you have 1,000 images and only one of them shows flooding. So now you can imagine that even if you have the best possible algorithm in the world, there will be some misclassifications. That means in those 999 images that don't show a flooding, you may still have some flood pixels that are, however, wrong. So it's very challenging from a scientific point of view to develop a system that is so robust to capture all these cases. The way how the system, the service approaches is that using 3 well-established flood mapping algorithms from our colleagues from the German Aerospace Agency, DLR, then colleagues from Luxembourg, from the LIST Institute, and also we're using one of the algorithms of TRD. And what we're providing is an output that's not just showing the flood extent layer, but we're also showing a likelihood layer. So how likely we detect flooding in a certain pixel. And we also tell the user actually where it's not possible to map flooding with the provision of so-called exclusion masks. Last but not least, we also provide advisory flags to tell them, well, be careful in these environmental conditions, results may not be reliable. So the basic idea behind the algorithms is at the for the present time that we look for the one scenario shown here. Normally, if you have a land surface, we have a strong return from the soil surface that leads to rather high backscatter in the Sentinel-1 measurements. And now, if water is flooding the surface, that leads to a smooth surface, leading to forward scattering, predominantly and very low backscatter return. So for example, if you look then at the Sentinel-1 image showing a flooding, the areas that are affected by flooding are those shown with very low backscatter values, here shown in the black colors. This is the example of the Queensland flood in 2019. Now, that seems very straightforward, actually, but actually many things can go wrong. The first thing that can go wrong is that it's not just water that can show very low backscatter, but there are many water lookalike surfaces, like, for example, tarmac areas on airports. Sand deserts can have very low backscatter, grasslands during some parts of the year, or there can also be radar shadows that lead to very low backscatter characteristics in the image. There's also some dynamic phenomena, like, for example, if there's a freezing event and the whole land surface freezes, that pushes down backscatter to very low levels. And we can also have the situation that there's snow on the surface and becoming wet. That can also lead to very low backscatter conditions. So that such a scenario then leads to false positives, which can, of course, be problematic, particularly for the no flooding scenes. Secondly, we also have the case that there are no sensitivity areas. In the case of the SAR data, we have challenges where water is below a dense forest canopy. We cannot see through the canopy. So we will never be able to map water below this forest. We also have problems in urban areas, unfortunately, because that leads to very strong double bounce phenomena, really confusing the interpretation of the data. So SAR, in that case, if you just look at backscatter values, is very poorly equipped for mapping water in urban areas. And this is then, of course, problematic for flood scenes because that causes false negatives that we need to describe a priori for the user in order not to confuse them, because the areas visible seen, the flooded areas seen by Sentinel-1 are always lower than the real actual flooded area. The way how the three algorithms deal with this is done in different ways. As I said, the three algorithms that we are using in the GFM service come from DLR, from LIST, and from TRVN, and they all have a different development history, thereby probing the information content of the data in different ways. The three algorithms also distinguish themselves by looking either at the water, total surface water area, or only looking at the flooded area, or trying to combine both of them. The method developed by DLR is a hierarchical tile-based thresholding technique. Also for LIST, it's a very similar generic approach. In the case of the TRVN algorithm, we use a Bayesian inference method. The method also distinguished themselves by the way how the data being post-processed. DLR and LIST also have some region growing attached to the algorithm to refine the flood extent boundaries layers. Also, the way how we then estimate the likelihood is different. In case of DLR, they use a fossililogical approach, and TRVN, again, a Bayesian approach, as in this case also by LIST. Let me show you the idea behind the TRVN algorithm. The idea behind the TRVN algorithm is that we describe the backscattering characteristic for each individual pixel and compute the certain expected backscatter value for the day of year. Yeah, for example, looking here into an agricultural area in Greece and taking just one pixel from there, we see that backscatter in this pixel varies between around -13 dB up to maybe -7 dB, or here even higher. And that pattern basically follows the seasonal pattern on vegetation and soil moisture conditions. Only when there's then flooding, the values backscatter is pushed below a certain level to very low backscatter values, typically for surface water areas. So we describe the backscattering characteristics for each pixel with a so-called harmonic model. That, for example, would be the backscatter image on July 15th, and that would be the same image on October 15th, just representing differences, again, in vegetation and soil moisture conditions between those day of years. Yeah, and if then there's a flooding event, we get a certain backscatter value. And what we then do is we have like a probability distribution function describing the behavior of backscatter during that point in time. The behavior for the surface water backscatter is always the same. It doesn't matter. And then we use Bayesian inference to say what is the likelihood that that pixel is regularly like a normal backscatter conditions, or if there's flooding conditions. Yeah, let's show this with one concrete example here. So that's a SAR image. that was taken here on the 28th February of 2018. You see already here those areas that show very low backscatter in the order of -15 dB. And this is the image, the backscatter image, as we would expect it to look like if there's no flooding. Obviously, where the differences in backscatter between the real image and the expected image is very high, these areas are likely to be flooded. This is also then here our estimate based on the spatial approach for the flood posteriori probability. In this case, this probability derived from Sentinel-1 very nicely matches here with a flood delineation achieved with Sentinel-2. In order now to fuse the outcome of the different algorithms from DLR, LIST, and Theorin, we use what we call here an ensemble algorithm. So we have the incoming Sentinel-1 image. We apply algorithm 1, algorithm 2, algorithm 3. We both get a flood classification and a likelihood estimation. Yeah, this likelihood values are then combined in one separate stream here in a flood likelihood image as an ensemble. And the binary classifications are then also combined with all the exclusion masks to create an image that shows permanent water, seasonal water, like masked areas, and the decision flooded or no flooded. The realization of that algorithm in a workflow is actually quite complicated and quite demanding, because what we are doing is we have all the incoming Sentinel-1 image, then we do a certain pre-processing to make them fit for a data cube approach, so that we build up a multi-year Sentinel-1 data cube that can be used for doing a complete analysis of the backscatter history for each pixel globally, for all land surface areas, so that we derive harmonic model parameters. We can also derive all the different thematic exclusion layers. So this is done offline, and the results from the offline processes can then be fed into the online near real-time processing line. So the near real-time case, again, I do the 3 classification algorithms. I fetch data information from advisory flanking, output masking, put this into a ensemble algorithm, and out comes a product that contains all the layers as described before, like the observed flood extent, the total water area, the reference water area, the likelihood water, the exclusion mask, advisory flags, etc. To make this more concrete, here's an example shown for a flooding scenario for the River Rhine in Germany. So here you have the outcome from the DLR algorithm, from the LIST algorithm, and here from the Theorin algorithm. The reddish color here means that these are flood pixels. The dark blue means that these are the permanent water areas, so the river course, and there's some water bodies here near the river. And you see also here some like masking of surrounding areas. The green colors here show this is areas masked due to lack of sensitivity of backscatter to flooding. This could, for example, be forest areas, or it could in this case also be urban areas. We also mask for strong topography that are disturbing the SAR backscatter data in particular. There can also be a confusion with low backscatter areas like airport areas. In this case, actually, I think the low backscatter areas are shown actually real water bodies that were not contained in our reference water layer. And some very few areas are also affected by radio shadows, but this is not really strongly seen here in the image. Yeah, these results are taken together to produce then in the end an ensemble flood extent map. You see here the reddish colors plotted on top of a mean backscatter image. So you see how nicely that works out in this case. On the left, you see not the binary classification, but the flood likelihood layers. Also in this case, it looks very nice because the likelihood it decreases in particular at the borders of the water bodies. So that basically means that the flood likelihood also shows as mixed pixels, where there's water, partly water in there, but already a significant contribution from the land surface, making the classification more uncertain. But through this likelihood layer, we can more nicer visualize this. This is something also seen here in that example from a flooding in China, where through the use of the likelihood layer, we can follow the courses of the rivers and how flooding affected those areas along the river courses. If you would just use the binary classification, you might see flooding here, but not at the intermediate stretches of the river course. Yeah, and once we have those data, these results for individual dates, of course, we can start using acquisitions from several time stamps and start combining it to get a vivid expression of flood dynamics. For example, here's the observations we had from the Pakistan flooding in the year 2022. Where we had here an observation, for example, on the 18th of August, then here on the 30th of August, 11th September, 23rd of September. And taking all image stacks, we can start then mapping the day when the first flooding was noted in the SAR data. And we can also determine how long a certain pixel was flooded, so the flood frequency. And then this gives a very visual impressive image showing which areas have been particularly hit hard by the flood event. One example I mentioned in the beginning that motivated that work has been the flooding in Greece. Here you see the results from our algorithm over Greece. Again, here a sequence of measurements from the 6th of September, 7th September, 12th September, 13th, 18th, and 19th. How you could combine it to get an overview of the complete area that was affected by this particular flooding event. And here on the right, you see the flood frequency derived from these data. Okay, so far I've mostly told you what works nicely and highlighting the strengths of Sentinel-1 data for the mapping of flooding, flood dynamics. The big advantage, obviously, of synthetic aperture radar imagery is that we are not disturbed by cloud cover, so we can provide frequent coverage. And also, in the case of Sentinel-1, the mission is being designed to have to optimize coverage as good as possible on the global Earth surface. But as you know, a satellite cannot be switched on all the time. Like one cycle of the satellite from pole to pole takes about 100 minutes. From those 100 minutes, Sentinel-1 can be switched on for about 28 minutes, meaning we cannot get an even coverage of all the land surface areas, but somebody needs to make choices of priority areas. In the case of Sentinel-1, obviously one priority is to cover Europe as frequently as possible. The second preference for Sentinel-1 has been to monitoring tectonic active areas to benefit from the interferometric SAR capabilities of the mission. And then the last priority was agricultural areas to monitoring soil moisture conditions and agricultural production in those areas. And last but not least, some areas like, for example, Siberia or the desert areas have been covered the least. So we go from typical revisit times from 1, 2, 3 days over Europe to 6 to 12 days over less well-covered areas to revisit times that are even larger than the 12 days. Still, this is the best mission we can have to get a frequent coverage of the land surface at very high revisit times. Then we ask the question, okay, Well, from a GFM service, we know painfully that sometimes there are flooding events and a Sentinel-1 is not delivering us data. So we've checked a number of significant flooding events from a database. So in this case, we looked at 104 flooding events and we checked if the GFM service detected the flooding. And here you see the global result for those 104 flooding events. So if it's a blue circle, that means for that particular flood event, we saw images that depicted the flooding. But there were also scenarios where we looked at the data archive, and for the areas that were reported and the time period that was reported, we didn't find a single Sentinel-1 image. So there was no data for those flood events. And in other cases, while we had images within the denoted areas and denoted time frame, but they didn't show any visible flooding. So maybe there was something wrong with the database, or Sentinel-1 wasn't really able to pick this event up, or the timing was very unfortunate. So that's one limitation one has to be aware of. Another limitation of the GFM service is that at present, we only use one polarization from the Sentinel-1 satellites. Sentinel-1 acquires data in both VV and VH polarization. And just for computational effort reasons, we only use the VV polarization. However, that has the disadvantage that some of the flooding events may be missed that are nicely depicted in the VH channel. We have observed that in particular, VH can be very useful for detecting low vegetation that is covered by water. You know, here on the left side, you see the results from the GFM, and on the right, you see the VH image showing that in the VH image, the extent of the flooding is much more apparent along those two river courses than it is in the corresponding VV data. Okay, so now I explained you the GFM service and the approaches that we're using there, and now I want to explain is how I would advocate how we should fuse optical and radar data for have improved mapping of surface water and flooding dynamics. The first point I want to make is that usually the mapping of water is being treated as an image-oriented classification problem, meaning that you have this, that people have the view, okay, I take an image, I use all the spectral channels that I have in my image and solve a classification problem as good as possible. I think in case of surface water and flooding dynamics, we should shift more to a geophysical understanding and treat it as a geophysical variable retrieval problem. Meaning is that we focus on the physical process to depict it as correctly as possible, and that we make dedicated efforts of describing the uncertainties, accounting for both visible and hidden components present within the data. So what do I mean by this? So on the left, you see a SAR image from Sentinel-1 showing a flood scenario from the flooding in Germany in 2021. So if we now would just like to map flooding extent, that would be the right image. But as we do in the GFM service, I think it's important not just to map the surface water, but also to tell the users what are the areas where we can't do flood mapping. So put specifically all the masks on top of the image as well. So in this case, again, like as we had before, the greenish areas, areas where the Sentinel-1 data show no sensitivity to surface flooding. There's also topographic distortion areas, and you immediately see how many areas cannot be captured by Sentinel-1 due to these very influences. But if you would see that image, you couldn't even imagine what is the information content really of that image. You would only see what's apparent. Also, here's another example. for a flood that happened in Austria in, when was it? I don't know which year it was. But anyhow, it was a rather small flooding along a small river in Austria. But we checked the availability of Sentinel-1 and Sentinel-2 data, and we looked at the hydrograph for that river. It was just very unfortunate that during the flood peak, actually, we didn't have an image. We had an image before, we had an image afterwards. But as it was a small river and a rather short-lived event, that meant like only 2 days afterwards, we could only see a much smaller area that was affected by flooding. So you're really due to say, if the repeat coverage is not daily but longer, you miss a lot of dynamic surface water dynamics. And this combined with our incapability to look, for example, for forest, leads to a significant underestimation of surface water area. So with this background, we said, well, let's use the fusion of the level 2 data from optical and SAR data, and again, let's consider to have like fully independent processing lines, treating Landsat data, Sentinel-2 data, and Sentinel-1 data in a similar manner, and only start aggregating at the end. So again, meaning you could process Landsat data in one cloud platform, you could do Sentinel-2 processing in another platform, and again Sentinel-1 in a third platform. So you do all the steps before you do then the aggregation and fusion. So the inputs to these fusion algorithms are optical and SAR data, each containing separately the likelihood estimate for, like, do we observe water or no? It would combine sensor-specific masks, recognizing that an optical sensor has different limitations than a SAR sensor. And here comes again an effort that even if you have already a likelihood value, it still would be good to have like an uncertainty on top of the likelihood. Yeah, and then if you, for example, have one image from Landsat and one image from Sentinel-1, you could then make a decision tree to merge the two images if they're temporarily close enough to have a meaningful fusion of the two data. And then you could say, well, if I have in both image valid likelihood values, then I simply compute the mean of those two likelihoods, or I do an uncertainty weighted average. If only one of the satellites show a likelihood value, I take the one, thereby filling gaps in the other. And if both pixels are masked, well, I can't do anything about it, then also the pixel in the fused image is masked. So the output would be a more complete water likelihood map, a smaller masked area, and a reduced uncertainty of the output product. Now, if you have the question, how do I produce a likelihood value? Because, you know, it's not that straightforward. Most classification algorithms give you a binary result, not to speak of a likelihood estimate or a precision estimate of your likelihood estimate. Obviously, there's different approaches to this depending on the basic choice of the algorithm you're doing. But in the end, there's multiple methods of how you can solve this. There's, for example, Monte Carlo methods for solving it. There's Bayesian inference methods. There's fuzzy logic. Yeah, for example, here in this picture is shown a very interesting approach that Muhammad has proposed. While he's trained a neural network, a UNet, for doing flood classification for both optical and SAR data. Once the UNet is trained, you can also actually manipulate the network by switching off certain nodes within the networks, so thereby producing outputs and simulating certain uncertainty in the model estimates, so that you would then get a distribution of likely outcomes. Yeah, so that here I want to show you now a first concrete example how this could look like. This work is from David De Vesta and Muhammad, and the article is in preparation. On top, you see the water probability from Sentinel-1, Sentinel-2. The white areas that are shown here are those areas that are masked in the data. So let's first look at the masked areas. You see here in the SAR data, more areas are masked than in the optical data. Yeah, optical data are particularly masked for high vegetation areas where we cannot see through. And for Sentinel-1, it's also topography that has a very important effect on how we do the masking. We can also then look at the likelihood values. Like at first sight, they look very similar for that case. But if you look into details, there are quite significant differences. Yeah, for example, here in that case, that small little river arm, we don't have any Sentinel-1 observations, possibly due to the specific geometry for that scene in that urban area, while for the Sentinel-2 data, we're still seeing it. On the other hand, it's interesting here in the part of that coastline that Sentinel-2 is masked, most likely due to high vegetation, while we still have some capability from Sentinel-1 to map it. The uncertainty here in those areas from Sentinel-1 is also higher, but we still do have an estimate. Yeah, and if we now start combining those two likely values from Sentinel-1 and Sentinel-2, we get a more complete image with less areas masked. In the end, with the areas that are left over for the masking, like urban areas here along that river and some part where there's really dense vegetation, but overall the mask is much reduced. And overall, all the features of the surface water in that case can be much better distinguished. Below, you can also see how the precision estimates that also show some sensor artifacts in both cases. By fusing them, how they can be reduced in the fused product. So that in the end, we get an improved representation of the surface water body. Yeah, and like particularly those people who like working with optical data, they often like to highlight that, you know, using optical data can give you more robust classifications, which is true. I mean, it's more difficult to work with SAR data, and it's more difficult to achieve as good classification accuracies as it is with optical data. But it always kind of implies that we need to find optical data that are cloud-free and not impacted by any kind of atmospheric phenomena. So, for example, if you have another example, here's a river, here's a forested area, here's some agricultural area. If we have a scenario like a Sentinel-2 image that is cloud-free, we get very good classification accuracy for that image. With a very high intersection over unit score of 90%. For Sentinel-1, the intersection over unit score is lower than for Sentinel-2. And if you fuse them, the combined product is also not much better than it is for Sentinel-2. So as a Sentinel-2, an optical person, you could now say, well, why would we then use SAR data if I can already achieve it the same accuracy with Sentinel-2 alone? But it's very clear if I would take another date from Sentinel-2 that is affected by clouds, it has an overall impact on the completeness of the water masking. It also has an impact on the accuracy of the water masking. So in this case, for example, Sentinel-2 achieves a higher accuracy. The accuracy achieved with Sentinel-2 is much lower, with an intersection over unit of 59. But if I combine them, again, I get very good results. Yeah, with this, I come to the end of my presentation. So thanks, I would like to highlight that thanks to the open data policy adopted by space agencies, for many optical and SAR datasets, our capabilities for monitoring water body and flood dynamics have increased tremendously. Yeah, so we it's really a great resource that we have with Landsat Sentinel-2 on the optical side, and on the SAR side, Sentinel-1, and now also recently we've started to have data from the NISA mission from NASA and the Indian colleagues. I would advocate that we should get rid of our idea that we do a classification of water bodies, but I would urge to regard water features as a dynamic hydrological process that can change very quickly. So the water body and flat mapping, to my point of view, should be regarded as a geophysical variable retrieval problem that also provides mass and uncertainty estimates, and not just tell us where water is observed or not. Yeah, and once we start wanting to fuse different data sets, again, I really like being a physicist. I like being transparent at what we're doing. So I find it much more traceable if we first process each individual source separately, so that we can describe the strength and limitations of each data set separately, and then we can then have dedicated rules of how to fuse them with the knowledge of surface water dynamics and with the knowledge of the specific sensor, specific advantages and limitations. Yeah, and if we do this properly, I think we can make it almost as robust as if we throw all data into the classification approach, and we would have the additional advantage that we would have less data preparation and data moving around efforts. Yeah, with this, I would like to thank you for your attention, and I will be very happy for taking questions. So now I need to see what questions are there. Yeah, I start with one question from 50 minutes ago. So a colleague from Ethiopia was how river discharge could be generated from satellite data. Yeah, there's different approaches for measuring discharge. If you have very large rivers and water bodies, you could use techniques like altimeters that measure basically the echoes from microwave sensors. That's a specific technique, but again, very limited to very large water bodies or large transects of rivers. Recently, NASA and the French Space Agency have also launched the so-called SWOT mission. That's a swath-based altimetry mission, which is currently revolutionizing our capability for mapping river courses, their topography, and then also estimating river discharge. One disadvantage of the SWOT mission is that its repeat coverage is not as good. So capturing the dynamics will not be possible with SWOT. But then we could also use like these techniques I've been referring to, that we map the extent of, say, the rivers or water reservoirs, and with the knowledge of historic discharge data, you can calibrate models to go from observed surface area to observed discharge. I hope that answers the question. Then the next question from 45 minutes ago. So from a colleague, Holland, Yonaba. To see the whole question. Yeah, he points out the problem of mapping small water bodies in West Africa, particularly where water is highly turbid. Yes, that's one of the limitations, for example, that you might have with optical data. Again, many people, I mean, when you work, I'm coming from the field of SAR, so I'm a radar expert. And for us, it's always very obvious that it's even as a problem as they sound as simple, let's use SAR data for mapping water. It's not that simple. So we have always been aware of the disadvantages and advantages of the system. And we have also known that under certain conditions, you cannot do water mapping. But the same applies obviously to optical data, so that as an example you've mentioned, if the water surface is very turbid or if the water depth is very small, you may have also big challenges of using optical data for surface water mapping. And you might not be able to solve the problem just from the optical side. You might have to combine it with SAR data and maybe topographic information to correct this. You mentioned here stacking of multispectral images. Yes. If you go away from one image and look into a complete time stack, into a complete data cube, that also is a very good way of dealing with those challenges, because it could be, for example, that the turbidity of the lake only is only there for a couple of weeks, and then water conditions improve. Then you get to reliable mapping of the water bodies. Yeah, here's a question from 18 minutes ago from Avinash. So he referred to the Opera product from NASA. Yeah, also NASA has developed a very nice method for mapping water bodies. So they do not do flood mapping specifically, but they use Sentinel-1 image for mapping the complete surface water area. And the results I've seen from them is also very nice. They also use different kind of post-processing algorithms to deal with problems like over-detection and these things. We have not had yet the chance to compare results from the GFM with Opera, but I'm very much looking forward to this. I have to say that even within, say, the GFM consortium, we've started to compare results from the DLR algorithm with the results from the Luxembourg algorithm and our algorithm. Obviously, you can very quickly do this for the individual flood cases, but doing this on a systematic basis for more flooding events under different environmental conditions is very challenging. But only this is then highlighting the strengths and weaknesses of different approaches very nicely. Because if you just limit yourself to one case, one algorithm could have a specific issue with that case. And if you don't do more flooding events, that may actually represent the real strengths and weaknesses of different algorithms, not in a good way. So it's always important to look at different and many flood cases to make a decision how the different algorithms work. So yes, I'm also looking very much forward to compare the results to the Opera data in a very systematic fashion. Oh, there's many more questions. I've now just looked at the FAQ, but now I've also seen the chat. Okay, there's many more questions here. Yeah, okay, no, there's mostly about the recording and the transcript, but there's here coming a question from Taha Nassim. How can we map flooding in arid regions that are now experiencing more flooding due to climate change using SAR? Yeah, the mapping of flooding in the arid regions is particularly challenging for SAR because of the fact that like sand swallows the microwaves, so backscatter from sand can be also very, very low. So separating between backscatter from sand and the surface water or flooding is not really possible. So that's one of the real big challenges of using SAR data in arid regions, and there's certain limitations that are very difficult to overcome. Maybe one can work with different polarization, or maybe also use with different frequencies. So maybe areas that are impossible to map with Sentinel-1 will become mappable with NISA. Yeah, but we have to see. One approach that some people are using in desert areas is not to look at backscatter, but look at interferometric coherence. Interferometric coherence requires that you set up a processing line for matching SAR image pairs so the complex images, and doing INSAR, and you estimate the coherence. And the coherence essentially tells you if scattering properties have changed significantly from one image to the next. Yeah, results with this technique can be very nice in desert areas, showing you much more complete areas affected through the flooding. And I think, if you do this in a post-processing or offline processing mode, this is fine. From an operational point of view, it really becomes very challenging because INSAR processing efforts are very large, and not too many people are doing this fully operationally. I know that to some extent, colleagues from Alaska SAR facility and from NASA have started doing this and are also providing products. So maybe we are coming to a scenario that space agencies are not just providing backscatter data in an operational manner, but also interferometric SAR data in an operational manner. But we need to see how the massive budget cuts in the US that is affecting NASA and NOAA and all the space, different actors active in the Earth observation domain in the US, how this will have an impact. Then I have here a question from Alexandros Konis. Yeah, he asked about if we plan to incorporate flood depth to combine it with the optical and SAR data. Yeah, we've started at Theobin, we've started a little bit into this, but we're not really experts. So we will stay away from the topic, but I've seen now colleagues started working on this. For example, our colleagues from the Joint Research Center of the European Commission started efforts along the way, or colleagues at Deltares and other organizations have started this. Yeah, so I think this would be for me the next step. Because with the satellite data, we should describe as good as possible what the satellite is doing. But then, for example, to provide complete flood map, that should then be integrated into a model that obviously has to depend on some kind of digital terrain model so that you can complete the area that is flood affected. Obviously, I see this as a separate processing step or workflow after the satellite flood mapping. So again, to really be very transparent on where the information is coming from. I mean, sometimes when I see advertisements of commercial SAR data providers, you see images where you know that they can't come from a satellite alone. So these organizations already often use terrain models and hydrological models to complete the information that's coming from the SAR data, but selling it it's only coming from a SAR data. But yeah, again, what I argue for is that you make each step very transparent so that you also can trace errors in the whole processing, because this could obviously be very important for any kind of real world cases of if there was really water or no water. Then a student asked, how can false positives caused by surfaces like wet soils be tackled? I'm not sure if you refer here to a scenario where SAR data are affected or optical data. Yeah, in the case of SAR, actually a wet surface is really good for most of the time, because it means that backscatter is very high from the wet soil, so we can easily distinguish it from soils that start to be covered by water, after which the scattering mechanism changes fundamentally. I'm not so much an optical expert, but I could imagine that for the optical data, it's actually not that easy always to distinguish a very shallow surface water from wet soil spectrally. But I have not read yet enough articles to give you a confident answer on this. I'm not checking the other questions. Yeah, from the other chat, I see a presentation from Matthias. He says that he's working on an inventory of flood extent maps for flood forecasting. Yeah, and he notes that Sentinel-1, Sentinel-2 don't have many overlap dates. Yes, I would say so just for your region, but that's typically the case. So that in the end, if you look at the dynamic flooding phenomena, you hardly get any matching dates. And actually, one of the difficult things in validating data with other data sources is to find the scenario where the data were acquired at the same time and optical data didn't have any clouds. Yeah, and then you ask, how could I work with data fusion? I wouldn't call it specific. Again, if you consider the process as a geophysical process, and you have like maps in mind of river discharge, I would not per se start fusing them very early on. But I would rather build your models such a way that you can use each individual time step. But again, and then aggregating results on different time scales then depends on exactly what kind of model you would like to do. Again, be very careful in the way how you use the data, because they are not complete. They don't show the whole scenario. So just using Sentinel-1, so just using the optical and the SAR data for training an AI model comes with the disadvantage that the AI model learns all the errors in the satellite data, and not in the end will not present the flood fully correctly in later stages. So as I discussed in my comment before, so I think in order to do a fully correct interpretation, it would be necessary that you use the satellite data, combine it with some kind of hydrological modeling approach, and only then combine it with an AI algorithms to really describe the full process. Now switching again to the other one. Okay, thank you very much for your nice comments. Thanking me for the presentation. Yeah. Is there any more question? I'm not seeing it.
There are two new questions in the chat, Wolfgang.
There are two new questions. Okay. Here. Then a question by Rodrigo. What are the main differences between using the SWOT mission, Sentinel-1, and other remote sensing products for analyzing watermarks? I'm not quite sure what you mean by watermark. So, say in the concept in Austria, watermark is where a flooding has taken place. So, like how far the water has come during a flood scenario. Again, SWOT data is really beautiful data set. It's really the start of a new area in altimetry. So I expect there's lots of improvements in many ways of mapping inland water bodies and flood dynamics from this data. Currently, the main limitation is that the revisit time is so poor, so that in the end, you have to be extremely lucky to capture a flood peak with SWOT. I'm sure there will be scientific studies now then that show cases where SWOT hits exactly the right time. And then that will be, I think those SWOT results will be much better than the ones you achieve with Sentinel-1 or with NISA or any of the side-looking SAR systems. But again, just for completeness, it will be easier to map flood peaks with Sentinel-1 and NISA data simply because there's more data. Yeah, next question is from Amal. How has the fusion between SAR and optical data been implemented? Well, the example I've shown you is based on a Bayesian fusion. So basically, we used the estimate of the likelihood and the associated uncertainty in a Bayesian framework to come to a best estimate of likelihood and a reduced uncertainty estimate. We're still working on the best ways of doing it. So for us, it's just a start right now into research activities in this area because one has to be very careful on how you do this. Just as an example, I mentioned in my talk that, for example, the information we have from the VH channel from Sentinel-1 can be extremely useful for mapping flooded vegetation. Yeah, having said this, I certainly want to start combining VH data and VV data for flood mapping. But there's a but, because we also know that if you use VH data, that we have more cases of false positives, so of cases of over detection. So sometimes VH channel leads us to some wrong conclusions. So even like using the VV and the VH channel, I want to do it in this way that we consider VV and VH separately in a first step and only then start using them in the same way as I described between optical and SAR data. And we still need to look more into detail how to design the fusion algorithm in such a way as to take most new information content out of the VH data while making sure that the errors in the VH data do not spoil the good VV results. So that's open research question. The result, I mean, even with the simple Bayesian approach that we're using now, results already look good, but I'm pretty sure that one can improve on those methods. Okay, now I'm checking again the other chat. Well, now I'm not seeing any new question. Is that correct?
Yes, that's correct.
Good. Then, yeah, I would like to thank you very much for your attention. I'm very happy that so many of you stayed until the end of the sessions, of the question session. Yeah, and I hope I've inspired you in your work and the way how you work with the satellite data. And I wish you much success in using it for improving real world cases out there. Thank you very much for your attention. Goodbye. I stay in the chat if somebody wants to talk with me personally.